What really goes on inside a reaction? What are intermediates and transition states? And why are they so important? And why did I get so excited about this coloured blob? It's turned blue too. Keep watching to find out. Oh, and if you want to find out why a common error in textbooks wasted 2 weeks of research time for this video, be sure to hang on for the bonus extras at the end. Now, chemistry is about taking the materials of our world and bending them to our will. And to do that, we need to really dig into the details of chemical reactions, find out exactly how they work, and bend them to our will. I mean, adapt them to make impossible reactions possible. Now, when we write out a reaction like this, it looks really simple. This bit here just changes to this bit here. But most reactions, including this one, are actually way more complex than they look. This reaction, which is the hydrolysis of acyl chloride, is actually made of a sequence of 3 reactions that happen in a chain. Now, at first sight, it looks like we've just made everything more complicated than it needs to be. Why not just stick with this simple single arrow? Well, most of the time, that single arrow is enough. But once we get hold of these details, we can look for ways to change the chemistry and make a slow reaction fast or make an inefficient reaction efficient. And that is how we bestow our gifts of new materials to the worlds of medicine and engineering. Plus, it's just really cool. So today, we're going to look at this fairly simple reaction and see exactly how a catalyst will speed it up, even though that takes an extra 2 reactions. And as we go, we're going to be looking at these coloured electropotential maps to see precisely what it is that the catalyst does. So let's start here. This molecule is called acyl chloride and it's made up of 3 important parts. Here we have a simple methyl group. You probably recognize it as basically being methane with something stuck on the end. Here we have an oxygen atom doubly bonded to a carbon, and we're going to call this carbon atom a carbonyl carbon and this oxygen atom a carbonyl oxygen. Don't worry about what carbonyl means for now, it's just so we can keep track of which atoms we're talking about. Now, oxygen is the thug of the periodic table. It's in the top right, meaning it's very electronegative, which means it pulls all the electron density towards itself with what we call an electron withdrawing effect. And when it's doubly bonded to an atom, that whole withdrawing effect is concentrated on that one atom, in this case the carbonyl carbon. But the carbon atom's woes don't finish there. It's also bonded to chlorine. And chlorine is just one step to the right and one step down from oxygen. Its electronegativity is very similar to oxygen's, but it has to spread its valence electrons over a larger volume. So the poor carbon atom is having its electron density sucked away by these 2 very electronegative atoms, which leaves it with a partial positive electric charge. We can get an idea of how it works by looking at this electrostatic potential map. In this diagram, the more positive an atom gets, the more blue it becomes, and the more negative it gets, the more red it becomes, with green being neutral. And I know you know this, but just so it's said, those colours are just for illustration purposes only and are not the real colours of the molecule. But I know you know that. So here's our oxygen atom, and you can see the orange colour from where it's greedily hogging electrons to itself. The chlorine manages to be at least yellow, but it's so much larger that charge is more dispersed, and we see a dusting of neutral green on the outside edge here. Here is the carbonyl carbon, and you can see that the area directly over it has turned sky blue, which shows us the oxygen and chlorine are pulling away that electron density. And that effect is so strong, it even affects the hydrogens on the methyl group, pulling away their electron density too, as we can see from their slightly darker shade of blue. Now let's take a look at a water molecule. You probably already know that water is very polar because that thuggish oxygen just pulls all the electron density off the two baby hydrogens, which means the oxygen in water has a strong negative partial charge. So, we have a strong negative partial charge on the water and a positive partial charge on the carbonyl-carbon. So the water-oxygen atom gets attracted close to the carbonyl-carbon, but that's it. It can't get any closer because the carbonyl-carbon is fully bonded, and nothing else is going to leave to make space for that water molecule. If, however, the water molecule gets a solid kick from one of its neighbouring solvent molecules, it can get close enough to push its way in, and the chlorine might get kicked out, taking an electron with it and leaving as a chloride ion. But most of the time, the chlorine will just come straight back and the water will just get kicked back out again. But if the water molecule loses a proton and becomes a hydroxide ion, or if it just turns up as a hydroxide ion in the first place, well, now it has enough charge density to kick out the chlorine for good, and our acyl chloride becomes acetic acid. That is how water substitutes chlorine in acyl chloride to make acetic acid. But it's a slow process because it depends on how much water is around in our solvent, and even if we do the reaction in pure water, it's still going to take a relatively long time at pH 7. So what if this reaction is too slow for us? Or if we want to make it work at a lower temperature? And there could be many reasons for that. In industry, time really is money, and we often need to protect sensitive parts of a molecule by keeping the temperature down. In this case, we'll have to use a catalyst. And the one we're going to look at is boron trifluoride. Now, boron can't fill its valence shell by simple covalent bonding, which means it has space to receive an extra pair of electrons from another atom, so boron's always on the hunt for spare pairs of electrons. But this boron atom is attached to 3 fluorine atoms, and that amplifies everything. Because if oxygen is the thug of the periodic table, fluorine is the psycho. And when we look at the electrostatic potential map, we can see the boron sat right in the middle with those 2 exposed surfaces of strong partial positive charge. And pretty soon a water molecule will come along and bond to it. It's partially positive and it spies that lovely blob of negative charge on the carbonyl oxygen. The attraction pulls it in and they bond. Or they would. But there isn't room for 5 atoms on this tiny boron atom, so it has to choose between the 2 oxygens. Sometimes it'll just leave again with the water, but this time it bonds to the carbonyl oxygen and the water has to leave. So now we have our BF3 catalyst sitting on the carbonyl oxygen, like a face-hugging alien. Now let's go back to the electrostatic potential map and see what that's done to the acyl chloride. Let's look at the BF3 moiety first. Our fluorines are orange with partial negative charge as we expect, but the boron is green now because it's leaching electron density from the carbonyl oxygen. It's also gone green because those 3 fluorines are even stronger at pulling electron density away. And now, let's take a look at the 2 carbon atoms. The carbon atoms were mostly green before, but now, with these fluorines attached, the whole area has turned deep blue. And if you think that's bad, just take a look at this chlorine. It's turned blue too. That's not right for an atom in the top right of the periodic table. So this carbonyl carbon is now strongly partially positive. It's exposed and vulnerable to anything out there looking for positive charges, like water. Attracted to the strong partial positive charge on the carbon atom, it spears it with a pair of electrons. That was quite hard to do before, but now, with the destabilizing effect of those 3 psychotic fluorines, it's all up for grabs. Soon after this, however, the water oxygen realizes it's bitten off more than it can chew. With 3 bonds now, it's spreading its own electron density too thin, getting a full positive formal charge in the process. So it passes a proton to a neighboring solvent molecule and everything relaxes into acetic acid, but with the boron trifluoride still attached. Now the boron isn't just going to leave, so it hangs around until another water molecule turns up from behind, and then it might go back to being BF3H2O. But once it has gone, we finally get our acetic acid product. So that's the catalyzed mechanism in detail. And let's see what happens if we take that apart and look at the pieces. We start with our first reactants, the acyl chloride and BF3H2O, which react to make our acyl chloride BF3 complex in the first step. That complex is our first product, but it's not our final product, so we're going to call it an intermediate product, or just an intermediate for short. In the second step, water attacks the carbonyl-carbon. After losing a proton from the water, we get acetic acid BF3 complex as our second intermediate. And then finally, in the third step, boron trifluoride is picked off by another molecule of water to leave the final product, acetic acid. Now, there are some essential points to understand here. Firstly, the intermediates are real molecules that exist for at least a tiny amount of time, and if we're quick enough, with expensive enough equipment, we can detect them in our reaction mixture. Secondly, in this case, our intermediates successively lose energy and become more stable, but that isn't the case for all reactions. Intermediates can be higher or lower in energy than their precursors, but what affects the energetics of the overall reaction is only the difference in energy between the initial reactants and the final products. It doesn't matter how high or low the intermediates are, because in this sense, multi-step reactions are like a roller coaster. However much energy you put in to go up is how much energy you get back when you are going down again. Finally, using a catalyst does not change the energetics between the initial reactants and final products. Just as it doesn't matter if I go up the stairs or take the lift, the difference in potential energy between standing at the bottom and standing at the top will always be the same. In other words, a catalyst just helps you get to the same place faster. So, what's the point of using a catalyst to do in 3 steps what I could do in just 1 step without the catalyst? It's time to talk about transition states. But before we do, if you could just click the like button, it'll help us make more videos. Thanks. Now, when we look at the energy diagram for our reaction scheme, you can see that there's gaps between the intermediate and product stages, and it's transition states that come between those stages. But why is understanding them so crucial to making impractical reactions practical? Well, let's fill in this diagram and take a look. This line is the minimum amount of energy the atoms must have to make this arrangement. To keep things simple, let's say it's the potential energy they need to make those bonds and have that geometry. They can have more energy than that, and that's the kinetic energy they get from the heat of their environment. But they must have at least the energy of the blue line to transform themselves from the reactants into the products. Now you can see that our energy diagram really does look like a roller coaster, with 2 shallow bumps here and a great big one over here. But the roller coaster analogy only gets us so far. Another way to think about molecules moving from one side to the other is that they're like rubber balls. That's because molecules don't usually have enough energy to get over those bumps. Rather, they get it from their environment by getting knocked about by other molecules, and how often that happens depends on the temperature. The energy needed to get over these bumps is called activation energy. And if you want to learn more about how that works, why not check out my video on activation energy later. Now, a transition state is the arrangement of atoms at the absolute peak of an energy bump. So in this reaction scheme, there must be at least 3 transition states, and here they are. Remember that in the first step, We have to detach the water molecule from BF3 and bond the BF3 to the carbonyl oxygen. Now, these two processes occur simultaneously, with the carbonyl oxygen bonding to the boron as the water oxygen detaches. That means there will come a point where the boron atom is suspended between the two oxygen atoms, with the electron density stretched right out between the two. We saw in the activation energy video that pulling electron density away from the nuclei like this takes a lot of energy, and so the arrangement of the atoms in a transition state will have a higher energy than the arrangement of the reactants or the products. In fact, the definition of a transition state is that it's the point of maximum energy as the reactants become the products. And that's why, in my opinion, they shouldn't be called transition states at all, but rather transition points. Now, once the bond forms fully to the carbonyl oxygen and the water has left, we have our first intermediate product. But we have to wait around for the intermediate to get enough activation energy to cross the next peak or activation barrier. How long we have to wait depends on the temperature and how much water there is in our solvent. Our second transition state comes at a point just as the water is coming in and the chlorine is leaving, where the electron density is maximally stretched out again. After that, everything goes downhill to our second intermediate, acetic acid, with BF3 still attached. So all we have to do now is remove the boron trifluoride in the reverse process of the first step. And here is the third transition state, which, as you can see, is basically the same as the first one, but with one important difference. It's way up here. It turns out that taking the catalyst off again is much harder than putting it on. And what does that mean? It means that this step will hold up the whole of the reaction. It doesn't matter how easy it is to get over the first two activation barriers, it's going over this highest barrier that's going to take all the effort. We can't attach that boron trifluoride until either the BF3 gets shaken loose or the water slams into it hard enough to make it leave. Either way, the atoms must get enough activation energy from their environment for this reaction to proceed. And to make things worse, while it's waiting, it might even bump into another chloride ion and go back a step. Since the whole process has to wait for the molecules to get over the highest activation barrier, this step is called the rate determining step. And this explains why understanding transition states is so important. If we know which step is the rate determining step, and we can usually find that from experiments, then if we can find the structure of the intermediates that come before and after, we can make estimates and models of the transition state. And once we've done that, we can find a way to reduce its activation energy and make our reaction even more efficient. In this case, adding hydroxide ions would reduce the activation barrier to almost nothing, greatly speeding up the reaction. In fact, hydroxide ions would just be a better catalyst than BF3 for this whole reaction. But there are often cases in chemistry where we can't use our first choice catalyst. So in this case, let's imagine that BF3 is the best of the rest. So, now we've looked at the intermediates and transition states of this three-step reaction, let's clear up some confusion that I see students making time and time again. The difference between intermediates and transition states isn't simply a question of whether they appear at the top or the bottom of an energy diagram. They are fundamentally different. Because an intermediate is found in a valley on an energy diagram, it is at least slightly stable, so it will exist for a finite amount of time. And as I said before, we could in theory detect it, and in some cases we can even isolate them. But because a transition state is only found at the absolute peak of the energy diagram, it will not actually exist for any appreciable amount of time. By definition, if it gains one quantum of energy, it will fall onto the product side, and if it loses one quantum, it will fall back to the reactant side. We can never isolate that exact moment, but we can model it on computers. Alright, so we've seen that adding a catalyst not only adds an extra 2 steps, but in this case, and most others, it comes with its own rate determining step, holding everything up. So what is the point? Well, let's compare our catalyzed energy diagram with the uncatalyzed energy diagram. And now we see the point. Although the catalyzed reaction has 2 extra steps and its own rate determining step, the activation barriers are all much lower than for the uncatalyzed reaction. Going back to our rubber balls analogy, we can see the difference that the lower activation barrier makes. It's so much easier for the balls to cross the lower barriers, it doesn't matter that there are 2 more steps that way. And the effect of activation energy on the rate of reaction is exponential, meaning that even relatively small differences to the energy of the rate determining step can make a huge difference to the overall rate of reaction. And that is why understanding intermediates and transition states is so important in chemistry. It means we can choose and even design catalysts to reduce the activation barriers that would otherwise hold everything up. So now you've seen how simple looking reactions can be made up of sequences of simpler elementary reactions. You understand the difference between intermediates and transition states, and why understanding them means we can get much better control of our reactions. But there's still so much more to say about these reactions. For instance, this reaction is fully reversible, meaning it can go backwards nearly as easily as it goes forwards. And there is so much more to say about catalysts and how they work. And when we put those 2 things together, we get to the mind-blowing world of how enzymes really work. I really do think enzymes are mind-blowing. And don't forget to hang around for the bonus extras if you want to know a little bit more about how textbooks often misrepresent transition states, or the shocking truth of this energy diagram. But first, don't forget this video is made at Kyushu University, one of the best universities in Japan. We have science and engineering courses in English, so check out the description for a link. So, what went so wrong while I was preparing for this video? Well, my original plan was to take this very simple textbook example reaction. It's hydrogen gas and iodine gas reacting to make hydrogen iodide, and here is the graphic from the textbook that shows 3 transition states and 2 intermediates. Lovely. All I had to do was run that through my modeling software to get the nice pictures and some numbers for the graph. The only problem was, this graph is a lie. Well, calling it a lie is a bit harsh, but it's a classic case of an educational example that effectively teaches a concept while not actually being true. You see, the concept of a transition state relies on the idea of moving from one stable state to another via the wholly unstable transition state. But that doesn't happen in this reaction. In the first step, we break an iodine bond, and in the gas phase, the atoms simply get less stable the more we break the bonds. There is no high energy transition state moment between the bonded atoms and the separate atoms. And it was basically the same for the other steps. So our intermediates might be intermediate arrangements, but they aren't intermediate products. And they certainly don't sit in a little valley of stability like this diagram claims. But this textbook example does teach the concept well, so I actually think the ends justify the means. And what is the shocking truth of this energy diagram? Well, very simply, it doesn't look like this. It looks more like this, and that's because the reaction actually has many steps involving solvents and whatever transition states there are buried within a very complex mess. So finally, don't forget to look out for upcoming videos on reversible reactions and more details about catalysts, and I'll see you next time.